So as you can see, this is a rope swing, which it's swinging from the top to the bottom. So if we were to calculate the speed of this rope swing, we would use a conversion of energy. So up here it would be gravitational potential energy, and when it gets down here, it would be kinetic energy. If you equal both of these energies to each other, you could then find the velocity, which we would want to find in this case. The question we are answering is, what speed will someone on a rope swing reach if she starts from a height of 6 meters and finishes at a height of 1 meter with no frictional forces? Remember that these heights are made up and they're not real numbers. So we are going to be converting our gravitational potential energy into our kinetic energy. So to do that, we have to know the formulas for these. So gravitational potential energy is mgh, and kinetic energy is 1/2 mv squared. So in order to convert them to each other from the top to the bottom, we have to equal them to each other. So we do mgh equals 1/2 mv squared. We could first divide both sides by m to make it a little bit simpler and cancel out the m's, as we do not have that in our question. So now we just have gh equals 1/2 v squared. Now, to get rid of the fraction, we can multiply both sides by 2, so that we have 2gh equals v squared. Now you could square root both sides to get rid of, or to get the v on its own. So you have rad 2gh equals v. So now it's time to plug in numbers for our variables. So we know that g is equal to 9.81 because it's a constant, and h, we can find that by subtracting our heights from each other. So from the top to the bottom, 6 and 1. So h is 6 minus 1, which is 5 meters. So now we can plug all that in to find our velocity. So we have 2 times 9.81 times 5, and the square root of all of that equals our velocity. So if you plug that into a calculator, you get that the velocity is equal to 9.9 meters per second. And that's our answer.
Wow, that sure looks like a cool ride. I'm gonna ride it. Wow, that was quick. Okay, well, it looks like a nice sunny day here in Valencia. I am currently traveling at a constant rate of 4.5 meters per second. All is good. I am now approaching the top of the hill, which lies at a 71.6 meters in altitude, where I am about to go down the hill, which has a slope of 61 degrees.
Watch your profanity.
Fun.
Holy Toledo, Batman! That ride really was the bee's knees. Great! Let's talk about some this. Use the formula for mechanical energy, which mass times gravity times initial height plus half of the mass times the initial velocity squared, and that will equal our mass times gravity. So I'm just gonna recap what went down here. Plus half of we got our mass times our gravity times our initial height plus half times the initial velocity squared. And that equals the mass times the gravity plus half of the mass times the final velocity squared, which we don't know yet. So that's going to give us 7/16 plus 10.13 equals negative 61 plus 1/2 of the final velocity squared. We're going to bring the 61 over by adding it along with the 10.13 and 716 to get 787.13 equals this. Now we're going to divide by 0.5, get rid of that 1/2, and that will give you 1574.26 equals final velocity squared. Now because it's squared, we're going to want to square root these guys, so that's going to give us 39.68 meters per second. But for all you Western folk, that converts into 88.76 miles per hour. Yeehaw!
Stop! Wait a second. Neo, how are you using your hands to stop the bullets without using your hands to stop the bullets? Well, quite simple, Jonah. I'm applying a force. Wait, you're applying the force? No. I'm applying a force. It's a mass of an object multiplied by the amount of acceleration. This in turn creates work, which occurs when force is applied to an object to make it move in the same direction that the force is acting. Wait a second, but by that definition, isn't Neo's force acting in the opposite direction? Nope, it's still a force. Thing is, when two forces come together that act in different directions, we call that a collision, and whichever force is greater will continue moving, changing the direction of the lesser force. Yeah, but you're not changing the directions of the bullets, Keanu Reeves. How are you applying a force without it going in the opposite direction, even if you're applying a greater force on the bullets? Well, technically there are two different types of forces, elastic and inelastic. An elastic collision loses none of its momentum or kinetic energy during the collision, but no collision can be perfectly elastic since energy is always lost through heat or sound or stuff like that. And an inelastic collision loses some of its momentum or kinetic energy during the collision, either being absorbed by the other force or being equivalent to the other force, so that the momentum cancels entirely. This state is known as kinetic equilibrium, not only because the two forces are equivalent, but also because the momentum and energy in the collision are lost, creating a total exchange of 0 newtons with quickly dissipating kinetic energy. So, you and the bullets had an inelastic collision, in which you applied an equivalent force so that the energy of the bullets left the collision to come to a complete stop? Precisely. Let's look at the clip to wrap this all up. Let's ignore wind resistance and barrel diffraction, and assume that the bullet has a mass of 0.05 kilograms and is accelerating at 800 meters per second squared. The bullets would have a force of 40 newtons, which doesn't seem like a whole lot, but speed and density are what make it deadly. If Keanu were to have a 1 kilogram hand, or about 2 pounds, he would have to accelerate his hand at 40 meters per second squared to have the 40 newtons to stop the bullet. Therefore, since the forces are equivalent to each other, there would be no momentum stopping the bullets. Sweet, I think that just about covers it. Now you're gonna explain how you learned how to fly in the second one, right? Nope, gotta go. Thanks for watching, bye.